Welcome back to Applied Advanced Calculus. My name is Nathaniel, and today we are going to be looking at surface integrals, also known as surface areas, and flux through a surface. This is week 8 of this course. So surface integrals, also known as surface areas. The first thing we want to do is we want to get our function in terms of x and y's. Then, to find the surface area, we simply want to do the double integral of the square root of 1 plus di f over di x squared plus di f over di y squared, all of that times dA. And we also see that square root of 1 plus di f over di x squared plus di f over di y squared times dA is also known as ds. That's a very important part that we want to keep in mind for when we are going to be calculating flux later on. It's also important to understand all the different kinds of shapes that we are going to see throughout this course. We have a cone, which is shown by x squared plus y squared is equal to z squared. The fact that it's equal to z squared means that the cone is pointing in the z direction. The top half of the cone is expressed by z is equal to square root of x squared plus y squared. A cylinder, on the other hand, is written by x squared plus y squared is equal to r squared being the squared radius of the cylinder. And the fact that we don't see any z in our equation means that it is pointing in the z direction. If we scroll down, we can also look at elliptic paraboloids, which are expressed by x squared plus y squared is equal to z. The fact that it's equal to z means that the paraboloid is pointing in the z direction. Finally, we also have a sphere whose equation is x squared plus y squared plus z squared is equal to a squared. So let's look at an example. To find the surface area of the paraboloid z is equal to x squared plus y squared that lies inside the cylinder x squared plus y squared is equal to 4. The fact that it's equal to 4 means that the cylinder has a radius of 2. And both of them are pointing in the z direction. So if we're to plot this out, we would get, as we see on the right, this little graph over here. And the intersection of both is a circle, as you could see in the graph. To move on, we know that z is the same as our fxy, which is equal to x squared plus y squared. If we calculate our ds, it's going to be square root of 1 plus di f over di x squared plus di f over di y squared, all of that times dA, which is going to give us square root of 1 plus 4x squared plus 4y squared dA. Then, since our intersection is a circle, we could plug in our polar coordinates. So if we plug in x equals to r cos theta and y equals to r sine theta, we get square root of 1 plus 4r squared dA. Finally, to find the surface area as the question asked, we are going to do the double integral of ds. The outside integral from 0 to 2 pi, since it is a full circle. The inner integral from 0 to 2, because the radius is 2 for the cylinder, and ds, which is square root of 1 plus 4r squared dA, and dA is r dr d theta. Finally, we evaluate the double integral, which we know how to do based on previous videos, and we get our final answer as shown below. Let's move on. Now we are going to look at the flux through a surface. So the first thing we want to do when we have flux is, again, we are going to calculate our ds, which is square root of 1 plus di f over di x squared plus di f over di y squared times dA. dA, again, is either dx dy, or in polar coordinates, it's r dr d theta. Our n is going to be the gradient of g over the magnitude of the gradient of g, g being expressed through the plane. And finally, our flux is going to be the double integral of our f times n times ds. Let's look at an example to better understand. Over here, we are given V is equal to minus 4i minus 2j plus 2k through a rectangle. And we are asked to find the vector field, the flux of the vector field, in fact. So what are we going to do? Well, first we have 4 points. If we were to find the vector from B to A, we simply have to do B minus A, and that gives us a vector 0, 1, 0. If we apply that same logic for C to B, we get vector 1, 0, and minus 3. Now let's find the distance for those sides. If we find the distance AB, it gives us 1. And the distance CB gives us square root of 10. In case you don't remember, the formula to find the distance is the square root of xb minus xa squared plus yb minus ya squared. Once we find the distance, well, we have two distances. One going like this and one going like this. If we multiply both distances, well, that simply gives us the area. That considering that it's a double integral. Because we know for surface integrals, the area of the surface is the double integral of ds. So, we're going to multiply both distances, and that's going to give us square root of 10, which is in fact just our value for ds. Then we are going to take our two vectors BA and CB, and we are going to cross them. And that's going to give us a vector of minus 3, 0, and minus 1. Notice how at the graph in the beginning, the vector is pointing outwards in the positive direction. And our vector now is pointing in the negative direction. That means that that's simply the normal of the plane pointing in the opposite direction. So we are just going to factor out the negative. Finally, for our n, we are going to have 3, 0, 1 over the magnitude of that, which is square root of 10. Notice how square root of 10 shows up in the denominator over here. And we are going to multiply it by ds, which is square root of 10. Most times, ds is going to cancel out the denominator with n. Not all the time, but most of the time they cancel out. Finally, to calculate the flux, we are going to do the F times n times ds, which simply gives us a flux of minus 10. So that's all. I hope this helped you better understand surface integrals and flux through a surface. Make sure to practice. If this helped, make sure to leave a like and subscribe, and I'll see you in the next video. Thank you.